When we plan our network, we need to think long-term. At Meta's scale, it's rarely a case of consuming something that already exists. More often than not, we need to go out and build something from scratch in order to meet our often outsized needs. This can be a time-consuming process, so we need to think long-term and, where possible, identify opportunities to get ahead. One mechanism that helps us with this is our megawatts of compute forecast. And this describes the anticipated compute that we think we will have in the network at a future moment in time. This helps internal teams prepare designs and architectures to support the scale that's demanded by the business. And this is what this chart looked like at the end of 2023. And from a network point of view, we had plans in place to get us to 2030 and beyond. But while you might not fully appreciate from the chart, there was already quite a lot of work ahead of us in order to do that. However, as we progressed through 2024, we began to get increasing signals, upward revisions of these numbers that led us to reconsider our plans. It's no surprise that this came as a result of increase of AI workloads within our network, and this drives massive capacity increases in the backbone. And what this resulted in for us was a need to massively accelerate our original plans, pulling them in by multiple years in order to be able to support what the business required. But the question you might ask is, where do these megawatts come from? These additional megawatts come online predominantly through new data centers or through expansion of existing data centers, which typically comes by adding more buildings. In recent years, we've seen a massive acceleration in terms of the number of data centers that we have, particularly in North America, and you can see some of the announcements on the screen here today. Enabled with new technology and more scalable designs, these newer data centers are becoming larger and larger and more dense in terms of the power that's delivered per square meter. And this has significant implications for how we build the network. And in the next 20 minutes, Alberto and I are going to walk you through some of these challenges and what we've done in order to address them. But before we go too deep, a small primer might help. For those of you that aren't aware, this is the way that we architect our backbone. We have two different networks, CBB, Classic Backbone, and EBB, Express Backbone. We use Classic Backbone to serve our data center to POP traffic, and when we get to the POP, we then connect with external carriers and end users. This network is deployed all over the world to lots and lots of different types of locations, and the main power of CBB is that we're able to scale the thing up and scale the thing down to accommodate all of these different shapes and sizes of POPs where we need to deploy. EBB, in contrast to this, has a much larger minimum installation, and as a result, it's much bigger, and it's something that we use to serve all of our data center to data center traffic flows. In addition to this, EBB is a much more customized set of software in order to operate. We use an in-house routing protocol, as well as an in-house traffic engineering stack comprising of on-box agents that are programmed by a centralized controller. EBB network started in 2015-2016 timeframe, and before this time, we operated both CBB and EBB in parallel. And this diagram presents some of the major adoption and technology milestones that we encountered along the way. The most significant adoption for us, however, was in 2019, whenever we got to a point that 100% of all of the data center traffic flows could be moved to EBB. Alberto is going to talk through some of these key technology milestones as we go through the slides. And one thing that you'll see is that the same techniques that we've used to scale in the past can again be used to scale further in the future. In terms of traffic growth, this is a very simple depiction of the growth of the traffic in both of the networks, but I think it tells the story very well. While we see growth in both of the networks, the one that tends to present the hardest problems to solve and the most difficult challenges is the EBB network. And for the remainder of this presentation, we're going to focus on EBB and some of the techniques that we employed in order to enable this exponential growth. In terms of where we build data centers, you can see in the map a number of the data centers that we have in North America. This is just a subset. There's more, but the graph gets crowded. We build and operate our own optical network to interconnect all of these sites. And in addition to adding new data centers, we also have to support the growth of existing data centers, which may increase in size just due to more efficient servers or through more buildings being added to these existing sites. Our job in backbone engineering is to get these data centers reliably and redundantly connected to the rest of the network. And this can often be a challenge because sometimes building the fiber and connectivity into these sites can actually present many more challenges than building the building themselves. What we typically find are that the first couple of fiber pairs or the first couple of fiber paths into the site are relatively easy, but trying to get that third and fourth connection often results in us needing to use temporary solutions until construction can occur and we get these more scalable third and fourth paths. And the reason I mention this is we have some input into the site selection process, but there are many factors that influence this beyond just the ease of connectivity. So from a network point of view, anything that we can do to try and prepare to connect these data centers wherever they may appear on the map is of large value to the company. So the previous slides are mostly just a primer to give you some background on the existing network and the highlights that got us to this point. In the next section, Alberto is going to describe in more detail how we addressed the needs that I talked about in the beginning and the plans that we had to accelerate from 2028 into 2024 and 2025. After that, I'm going to talk about an entirely new opportunity that arose as a result of some of the things that were discussed earlier in the day. And then we'll close out with some key learnings and a preview of some future work. With this, I'll hand over to Alberto.
Thank you, Mark. As Mark mentioned earlier, network is not the primary factor for data center site selection. Historically, building fibers to new data center locations has been painful, especially when these fibers need to extend hundreds of miles. Just imagine the complexity of delivering fiber between New York and Chicago. The first technique to scale up to 10x backbone is to pre-build the components of the data center metro architecture. By pre-building them, we can more quickly provide connectivity to new data centers. First, we would build 2 rings of fibers that provide scalable capacity within the metro. After that, we will connect the long-haul fibers to the rings. Then, we will build 2 POPs that provide connectivity towards remote sites. Last, we will connect the data centers to the rings and therefore turn up capacity between data centers and POPs. By connecting data centers to POPs in the same metro, we can greatly simplify building data center connectivity. The second technique that we use for 10x backbone is platform scaling, which has 2 flavors, scaling up and scaling out. Scaling up heavily relies on vendor technology and it has primarily 2 forms. Larger chassis, where a 12-slot chassis provides 50% more capacity than an 8-slot chassis, and faster interfaces. By leveraging modern ASICs and line cards, we can double the capacity when we move from a 400 gig platform to an 800 gig platform. In contrast to the dependency with vendors in scaling up, scaling out is more under our control, and it has 2 flavors. Adding more backbone planes, going from 4 planes to 8 planes, results into doubling the capacity of the backbone. However, implementing this technique is quite disruptive and it requires a lot of planning and coordination, specifically when it comes to fiber restriping on all the backbone sites. Additionally, we can add multiple devices per plane. This technique is more sophisticated and allows us to scale capacity in a set of locations, as opposed to the global capacity increase from adding more backbone planes. This technique is also disruptive in the site where it's implemented. Scaling up and scaling out are not mutually exclusive, and in our 10-year 10x backbone, we have been using them both since 2017. In one particular site, we have more than doubled the platform capacity every year for the last 7 years, achieving a platform capacity that is 192 times the original capacity back in 2017. This was achieved with a combination of all scaling techniques. The third technique that we use to scale to 10x backbone is IP and optical integration. By leveraging CR technology, we are changing the power footprint per terabit in the network. In the first diagram, prior to CR, we have many transponders per router, and each of these transponders consumes up to 2 kilowatts of power. there is a clear demarcation between IP and optical layers. With CR, each of the plugs consumes 10 to 15 watts of additional power. However, by removing transponders, there is large savings in power. As a result of the CR plugs being installed in the routers, the split of IP and optical functions is not as clear as before. In summary, the use of CR transceivers increases the power consumption in the router, which is largely offset by the considerable power savings from removing standalone transponders. In aggregate, we use 80 to 90% less power when we use CR technology. To show the impact of CR technology in the network, we would like to show the space allocation in a midpoint with 80 rack positions. In our scenario, we have 50 rails. Each of the rails carries a capacity of 20 terabits and a total backbone capacity of 1 petabit. In a non-CR scenario, out of the 80 rack positions, we will use 50 of them for the optical network, 1 rack per rail. EBB will consume 8 racks with a total of 58 racks. In a 400 gig CR scenario, we don't have transponders, and we can land 4 rails per rack. This means that the optical network just consumes 13 racks. EBB remains the same at 8 racks, and to build the same 1 petabit of capacity, we just need 21 racks. It is worth to mention that the rack allocation between optical and IP goes from 90-10 to 60-40, where some of the racks that were allocated for optical can now be reused for the scaling of the IP platform. Additionally, having fewer devices enables us to deliver the same capacity with a smaller space and power footprint, or deliver more capacity with a contracted space and power. In an 800 gig CR scenario, we don't have transponders and we don't have codems either. And the routers connect directly to the ROADM optical device. In this scenario, to build the same 1 petabit of backbone capacity, we just need 6 optical racks and 8 EBB racks, in total 14 racks. In summary, by leveraging data center metro architecture, IP platform scaling, and IP and optical integration, we have transformed EBB from the experimental network in 2016 to a large-scale backbone that supports all DC-to-DC traffic at Meta. AI also introduced entirely new problems, and some of the 10x backbone work I just described was able to be reused to address those. Mark will talk about this now.
In the last 18 months, there has been huge interest in building larger clusters. It's been discussed multiple times today in multiple different presentations under a project called Prometheus. And the reason that this came up was we could see that we were outgrowing the power and space inside what was possible within a single physical location. So the most logical thing to do was to try and find other locations nearby where we could expand our reach and then interconnect these locations with network. In order to do this, we worked with our planning partners in order to identify sites of interest and determine how we could connect these at very, very high capacity and quickly analyze which sites worked for us and which sites didn't. And on the diagram, you can kind of see what this looks like. It's very similar to some of the slides you might have seen in the morning, but this is kind of a little bit more of the technical detail behind it. So what you can see is within the 3-kilometer radius, you've maybe got the ability to connect to some certain set of buildings, but as you go further and further out, you can connect to more and more of these things. And the way that we address this from a technology point of view is we use different types of plugs for 3 kilometers, 10 kilometers, and then we have a much more sophisticated, complicated solution when we go beyond 10 kilometers. We use optical DWDM technology in order to get this extended reach. Going into the 3 and 10 kilometer solutions in a bit more detail, from a networking point of view, this is relatively straightforward. Like, it's just choose the right type of plug, you get an added reach. However, one of the downsides of this solution is that every single fiber pair is only capable of carrying a single connection. So every single 400 gig or 800 gig, we need a pair of fibers. What this means is we need a lot of fibers. The interesting part is what you can see in these pictures. Gaia showed some of these in the morning, but the leftmost picture is what goes on inside one of our data centers. And you can tell this is an on-campus fiber duct bank because it's pretty close to the surface. They're not buried super deep because we control who digs the holes on this land. The other two on the right are what happens whenever we go between campuses within that sort of 3 kilometer to 10 kilometer range. And the middle picture in particular is the most interesting. So the bigger pipes that you can see here are 6-inch conduits. Each of those conduits will have 14 864 fiber trunks, which gives you a total of 12,000 fibers in each one of these pipes. So if you can quickly count this up and do the math, you very quickly get to hundreds of thousands of fiber pairs that are being laid between these different locations. And on the right, the final picture, what you can see is this is a vault. So this is how we get access to the fiber. So if there's a cut, they will go to the nearest vault, they will pull the fiber and kind of relay it. And these are built every 300 meters roughly. So you can imagine the amount of disruption it causes whenever in a region, whenever we start to build this type of thing. We have to close lanes of traffic, take up an entire highway. And there's a permitting part of all of this where we have to get permission from people to dig these holes. So this actually is the complicated part of the 3 and 10 kilometer solutions. If we look at the longer haul solution, this one is much more reliant on smart technology. So in this case, we will employ a DWDM optical system. And one of the primary benefits compared to the previous solution is we can multiplex using this technology 64 connections onto a single fiber pair. And what this means is a 64x reduction in the amount of fiber that we need compared to the previous example. And this is important because whenever we run longer distance, digging the holes that you've seen in the previous picture, like halfway across a state, that takes a lot of time. So for this type of scenario, we run a much smaller number of fibers, which we can do with a much, much smaller hole and with much less disruption. Other things that are interesting about this solution, we use an optical protection switch. I'm not mad about optical protection switches because it causes us some lack of transparency between the optical and the IP layer. But the beauty of this solution is it greatly reduces the number of IP interfaces we need on the routers if we were to do the protection at the IP layer. With this design, what we do is we take one of these systems, 64 times 800 gig, 51.2T, and we just horizontally scale that in order to get the desired amount of capacity. And for the links that we've talked about today, we're usually in around the 100 kilometer range, so we don't need to have any intermediate amplification sites at this point, which keeps this solution relatively straightforward. Just to underscore the scale of these interconnects, if it wasn't obvious from the pictures that I've shown you so far. So this backbone that Alberto talked about, that had all of this scale in the previous 10 years, one of these AI backbone site pairs will be double the size of our entire backbone network. And this presents many interesting challenges, mostly in how we deploy and provision the capacity. I think we've dealt with deploying lots of equipment at very, very high scale. But in terms of the number of fiber pairs that need to be terminated, particularly between the multiplexer and the router, this is going to be like a significant undertaking for us. I'm not sure if everybody's aware, but the ZR type of technology, it does tend to require the fibers to be very clean and much better handling than what you would typically expect within a LR or FR type of transmitter. So they're much less forgiving, which means we need to think hard about how we scale up that process of connecting them. So this is work that's in progress. So in terms of the next steps, or the work that goes on right now, there's still a bunch of work in terms of the permitting and the construction to connect all of these different sites. We need to qualify a bunch of new hardware. People that are in the industry will know that 800 gig ZR technology is new. Let's say the scale of production for all of these components is ramping. So we need to qualify all of those new components inside all of our different existing hardware and all of the tools and systems that will support this network. As I mentioned already, the scale of this means we need to think hard about where we can optimize the speed of deployment, particularly around like the cabling, installation, and provisioning of the equipment. Additionally, there's a very long-standing relationship between optical and backbone. We use common systems, common tools, common terminology. When we work with the data center team, it's still the same company, but many of the assumptions they have about how things work are slightly different. So we need to make sure that things don't get lost in misunderstandings of terminology, and we converge on the same operational practices and tooling in order to manage the network. And the final thing, I haven't talked about it much here, but in that protection switch system, there is a potential where if we have a partial failure, we can have a latency variation across different circuits. So we need to figure out, based on the exact designs, whether that latency is going to cause us a problem or not. And maybe we need to build some off-box automation to drain some capacity rather than keeping higher latency circuits in the network. With this, I'll hand back to Alberto to cover some of the key learnings for the entire session.
Thanks, Mark. Scaling EBB has been a wild journey over the last 8 to 9 years, and it is a story of unexpected acceleration where our scalability plans from 2028 had to be pulled into 2024 to meet the network demand. These are the key learnings. 10x backbone is possible because of the innovation in scaling up and scaling out. Using more powerful line cards, larger chassis, and more devices per site has enabled the scaling of the backbone. Pre-building scalable metro designs enables faster response to network growth, either by landing additional capacity or turning up capacity to a new data center. IP and optical integration reduces the number of active devices, and it also reduces the power footprint consumed by the network. Reusing 10x backbone technology enables the build of AI backbone, especially technologies like IP and optical integration and 800 gig CR. As we heard from Gaia in the morning and Mark earlier, Meta is planning to build city-sized data centers, and our backbone has to evolve and scale. To do this, we see leaf and spine architecture as the next step to scale out our platforms. This architecture provides with less disruptive scaling steps. Just imagine the complexity of restriping fibers from 1 device to 4 devices compared to the simplicity of adding a new set of leaves that provides additional platform capacity. Additionally, we will turn up AI backbone and iterate as we go to more sites. Throughout this process, we will understand AI intricacies as traffic goes through the optical network. This is all of the content for today. Thank you.